A laser is a device that emits light through a process of optical amplification based on the stimulated emission of electromagnetic radiation. The term laser originated as an acronym for light amplification by stimulated emission of radiation. In 1917, Albert Einstein first suggested the basic theory for the laser. Introduction to laser. The first laser was built in 1960 by Theodore H. Maiman at Hughes Research Laboratories, based on theoretical work by Charles Hard Townes and Arthur Leonard Shallow. A laser differs from other sources of light in that it emits light which is coherent. Spatial coherence allows a laser to be focused to a tight spot, enabling applications such as laser cutting and lithography. Spatial coherence also allows a laser beam to stay narrow over great distances. This is called as collimation, enabling applications such as laser pointers and LiDAR. Lasers can also have high temporal coherence, which allows them to emit light with a very narrow spectrum. For example, they can emit a single color of light. Alternatively, temporal coherence can be used to produce pulses of light with a broad spectrum but durations as short as a femtosecond, which is ultra-short pulses. In the classical view, the energy of an electron orbiting an atomic nucleus is larger for orbits further from the nucleus of an atom. However, quantum mechanical effects force electrons to take on discrete positions in orbitals. Thus, electrons are found in specific energy levels of an atom, two of which are shown below. An electron in an atom can absorb energy from light or heat only if there is a transition between energy levels that matches the energy carried by the photon or phonon. For light, this means that any given transition will only absorb one particular wavelength of light. Photons with the correct wavelength can cause an electron to jump from the lower to the higher energy level. The photon is consumed in this process. When an electron is excited to a higher energy level, it will not stay that way forever. Eventually, the electron decays to a lower energy level which is not occupied, with transitions to different levels having different time constants. When such an electron decays without external influence, it emits a photon. This process is called spontaneous emission. The emitted photon has random phase and direction, but its wavelength matches the absorption wavelength of the transition. This is the mechanism of fluorescence and thermal emission. A photon with the correct wavelength to be absorbed by a transition can also cause an electron to drop from the higher to the lower level, emitting a new photon. The emitted photon exactly matches the original photon in wavelength, phase, and direction. This process is called stimulated emission. Simply, we can make laser by picking a medium that has the potential for optical gain, i.e., an amplifying medium. Selecting a means of putting energy into that medium, i.e., an excitation system. Constructing an optical feedback system for stimulating further emission, i.e., an optical resonator. In contrast to conventional laser, we can make some strong light source from randomized media. This laser is called as random lasers. Random lasers are from the coherent light scattering from laser scatters dispersed in the laser die. When this system receives external pumping, we can control the coherent scattering, from which good and strong laser light can be obtained. For example, as shown in the right figure, disordered array of metallic nanoparticles on the semiconductor substrate can work for the random lasers, which make strong peak in the visible spectrum. In the photovoltaic effect, electrons present in the valence band absorb light energy and, being excited, jump to the conduction band and become free. In contrast, in the photoelectric effect, electrons are emitted from solids, liquids, or gases into vacuum when they absorb energy from light. The operation of a photovoltaic cell requires 4 basic attributes. First, the absorption of light, generating electron-hole pairs in active region. Second, the separation of charge carriers of opposite types at junction due to junction potential. Third, it will continue to diffuse away from the junction and can travel a distance on average equal to the diffusion length before it recombines. Finally, the cell collects those carriers to an external circuit. To understand the working principle of the photovoltaic cells, it is important to analyze its current voltage relation such as IV relation as shown in this plot. When dark, current increases with increasing the voltage. However, when shed by light, the current in the PN junction will be negative under the certain threshold which is called as open circuit voltage or V sub OC. The current is not zero even when there is no applied voltage due to PN junction. At zero voltage, there is non-zero current, which is called short circuit current or I sub SC. Using the IV curve under the light, we can calculate the maximum power generated by the PN junction, which is represented by the fill factor or FF here. Then, we can calculate the maximum power as a product of V sub OC, I sub SC, and the fill factor. The cell efficiency can be calculated by dividing this maximum output power by the input power, which is solar spectrum property. As shown in the right figure, for silicon solar cell, the maximum efficiency is limited 33% at 1.34 electron-volt bandgap. The maximum power efficiency limit is a function of the bandgap of the semiconductor employed for the PN junction. Photovoltaic cells are not necessarily to be PN junction as was used in crystalline silicon. Instead, PN junction photovoltaic cells, we can use PIN structure as used in amorphous silicon as shown in the middle figure. Or we can use organic solar cells with a structure composed of bulk heterojunction which is capped by 2 metallic electrodes or MIM structure. There is a good reference for the comparison of a variety of photovoltaic materials and structures as shown in this map prepared by NREL of the U.S. Department of Energy. They updated this map periodically by reporting the advanced efficiency with reproducibility. As can be seen in this map, there are a variety of materials for the photovoltaic cells. For example, we can find multi-junction cells hitting higher than 45% efficiency. Another type is thin film-based photovoltaic cells such as CIGSOD cadmium telluride cells hitting 23%. Nowadays, perovskite solar cells keep increasing their efficiency hitting 26%. Organic photovoltaic cells show relatively lower efficiency, lower than 20%, however they keep increasing the efficiency. The point is how we can further enhance the efficiency and reduce the processing cost. First, we can select acceptable efficiency, but very low costs such as thin film, amorphous/polycrystalline materials, organic solar cells. Second, we can select high efficiency, but high cost solar cells such as high quality crystalline materials, tandem solar cells. Finally, we can select light concentrator with high efficiency cells with optical concentration. For the cost, it is advantageous to select thin film-based photovoltaic strategy. A thin film solar cell, or TFSC, is a solar cell that is made by depositing one or more thin layers, thin film, of photovoltaic material on a substrate. They have notable advantages. They can save material costs. They enable usage of PV materials like amorphous Si and organic semiconductors. They can significantly reduce thin film solar cell thickness. This would also allow the large-scale use of scarce semiconductor materials such as indium telluride. They are suitable for industrial roll-to-roll production. Finally, it is easy to be integrated to buildings. However, it is inevitable for the thin film solar cell to lose the efficiency when the thickness is too thin. For example, as shown in the upper right plot, absorption rapidly decreases with decreasing the layer thickness. To overcome the thickness dependence, in bulk Si, light trapping is typically achieved using a micron-sized pyramidal surface texturing as shown in the lower right figure. For the thin film solar cell, it is possible to use nanophotonics to enhance the absorption, conversion efficiency, and reduce the reflection. For example, it is possible to use metal nanoparticle for the plasmonic effects which boost solar cell performances. By introducing metallic nanoparticles, it is possible to absorb more light thanks to the localized surface plasmon resonance of metal nanoparticles. For example, for spherical noble metallic nanoparticles, the extinction peaks are located in the range from ultraviolet, visible, or near-infrared spectrum, which is advantageous in absorbing the strong intensity of the solar spectrum. The metal nanoparticles also contribute to the elongation of the optical path length. Due to the metal nanoparticles on the surface, fraction of light is rescattered into the substrate as shown in the upper right figure. It is also possible to integrate metallic nanostructures such as a grating as shown in the left schematic illustration. As described in the plasmonics, metal insulate interface can host the surface plasmon polariton. However, simply irradiating the external light to the interface can't excite the surface plasmon polariton. To excite the surface plasmon polariton, it is necessary to provide additional photon momentum. And this can be done by introducing metallic nanograting with designated periodicity for solar spectrum. By forming the surface plasmon polariton, the effective absorption of the thin film can be strongly increased as shown in the right figure. Another nanophotonics strategy is spectral conversion. By spectral conversion, we can think of two different types. The first one is down conversion, which converts shorter wavelength light into longer wavelength light as shown in the left figures. The second one is up conversion, which converts longer wavelength light into shorter wavelength light as shown in the right figures. Due to nonlinearity, up conversion efficiency is very low such that quantum yield is smaller than 1%. We can use these spectral conversion strategies to convert ultraviolet and infrared lights into the visible light ranges. Considering a fact that the most of the solar spectrum exhibits the strongest intensity in the visible spectrum, and therefore, it would be advantageous to use the spectral conversion strategy. In addition, we can employ nanophotonics approach to enhance the spectral conversion efficiency, which will in turn, enhance the photovoltaic efficiency. For example, we can use metallic nanostructures or particles which can be integrated with spectral conversion materials such as thin films or particles in the thin film solar cells as shown in this figure. The metallic nanostructures will provide plasmonic resonance and induce strong near field for the spectral conversion materials, which will boost the energy conversion efficiency.